Hello and welcome to another episode of Classes with Atish. In our last video on collisions, we were talking about one special problem that I wanted to cover in a separate video. So now is the chance to go over that. Okay. So first let us restate that problem. So there is a frictionless surface and there is one mass, let's call that MA, traveling with velocity VA, and then there is another mass which is MB, which is traveling with velocity VB. VA is greater than VB, so obviously after some time mass A will catch up with mass B. This mass B has a uncompressed spring attached to its end. The spring constant is K. The question is, one, what is the maximum compression of the spring? And two, final velocities after the collision has happened. Okay. So to solve this problem, we will break this problem up into a couple of steps. So this is the initial step during approach. Now, when mass A just comes in contact with the spring, it will still have velocity VA and the mass B is still having velocity VB, but right after that instant, when it starts to compress the spring, what will happen? So let's look at that situation. So this is mass B, it has the spring attached to it. Now it's a little bit compressed, okay. Let's say it is compressed by a distance x, okay, and mass B is here, okay. Okay. Now as soon as some compression happens, there is a spring force that will start acting on mass A. So if mass A had gravitational pull, it had a reaction from the frictionless surface. But now what is happening is there is a force Kx which is dependent on how much the compression has happened. X is a function of time obviously. Okay. So there is some deceleration of mass A, okay, and similarly for mass B there is some friction, there is some force of gravity, there is some reaction force, but mass B is getting a force Kx which is the spring force in this direction, which is increasing the velocity of mass B. So here it was VA. Let's say here it is VA dashed and VB dashed. So VA dashed is actually less than VA and VB dashed is greater than VB. Okay. Now how long will it keep on compressing? It will keep on compressing as long as A's velocity is greater than B's velocity. So the key here is the maximum compression will happen. Maximum compression will happen when both velocity of A and velocity of B are same. So the relative velocity is 0. So that is the time when maximum compression has happened. Okay. So let's say both of their velocities is V. This is mass A, this is mass B, and the spring has so far been compressed from its original state by x max. Okay. After that what will happen? So still the spring is compressed, still there is some force on in this direction Kx, in this, at this point it is Kx max on A and there is Kx max on B. Now after this state what will happen is A will slow down, become slower than this common velocity v, and B will speed up it will have more velocity than at the maximum compression, and that is the point when A loses contact with the spring. A will no more have any effect of a decelerating force. We have to find out the velocities once A loses contact with the spring. Okay? So, let us look at this situation now. In this situation, what we can do is, now if you realize mechanical energy is conserved between this initial state and this state of maximum compression, right. Why mechanical energy is conserved? Because in the x direction for the system A, B and the spring, there is no external force. Okay. So, if there are no external force, only force that is there is this internal force, which is Kx in the x direction. So, the spring force, and that is internal force. So, whenever there is no external force or non-conservative forces, then mechanical energy is conserved. We can say the total kinetic energy plus potential energy in this state will be equals to the total kinetic energy and potential energy in this state. Okay. So, we can then apply conservation of mechanical energy . So, Ke initial plus Pe initial will be equals to Ke final plus Pe final. So, initial state kinetic energy is half ma Va square plus half mb Vb square. Was there any potential energy? No, the spring is not compressed. So, potential energy is 0. In this maximum compression state, the total kinetic energy will be ma plus mb, and both are moving with this common velocity v square, plus there is a potential energy, and that is the spring potential energy, which is half k x max square. So, from this we can cancel out the halves and we can get x maximum square as ma Va square minus v square plus mb Vb square minus v square divided by k. Or we can write the maximum compression will be root over ma Va square minus v square plus mb Vb square minus v square by k. Okay. So, we found out the maximum compression of the spring. Now, we still do not know V. We had assumed some value of V. We can use conservation of linear momentum as well. Linear momentum is conserved everywhere, right? Not just the final and initial state. So, from conservation of linear momentum, initial linear momentum Pi will be equal to final linear momentum Pf. Now, Pi is MaVa plus MbVb, and P final is Ma plus Mb into V. So, from that V we can get as MaVa plus MbVb divided by Ma plus Mb. Now, if you substitute V here, you actually get the maximum compression in terms of Ma, Va, Mb, Vb and K. So, now we can say we found the maximum compression of the spring. Okay. Now, let us look at final velocities of A and B after collision. So, after collision has happened, the next stage will be what? So, Va Ma will be moving with some velocity, let us say Va double prime, and Mb is now the spring is totally uncompressed and it has left contact with A, and this, let's say, is moving with some Vb double prime. So the sequence of events, I drew it from right to left, but this is the sequence of events. Okay. Now this is a case of elastic collision, right? Now the initial state is this and the final state is this. In elastic collision, we know that both kinetic energy and linear momentum both are conserved. So from that, we can very easily now write down Va double dashed and Vb double dashed using two equations. One is their relative velocity of approach, Va minus Vb will be equals to the relative velocity of separation, Vb double dashed minus Va double dashed. Okay. This we come to this conclusion from applying conservation of linear momentum and conservation of kinetic energy. And from conservation of linear momentum, we can write MAVA plus MBVB will be equals to MAVB double dash MAVA double dashed plus MBVB double dashed. Okay. I will not work out the steps, but you can find out Va double dashed and Vb double dashed minus M2 MA plus MB Va plus 2 MB divided by MA plus MB Vb, and this one will be MB minus MA plus MB Vb plus 2 MA plus MB Va. So I have done this derivation in a previous video. I will link it up here. You can look at that. But that is how we get the final velocities of A and B after collision. Okay. So hope this makes sense, and the only key here is to understand the stages, what's happening with the spring. So as soon as A starts to compress the spring, there is a spring force which starts to accelerate MB, increase its velocity, and decelerate MA, decrease A's velocity, and there will be a stage at maximum compression when both their velocities will be same. So at this stage, if you apply conservation of mechanical energy and conservation of linear momentum, you can get the maximum compression of the spring. Okay.